All right, so we're going to look at the polynomials with real coefficients of degree n or less. The standard basis for these guys is just the monomials x to the k, where k ranges from 0 up through n. We're going to convert this into an orthonormal basis using the Gram Schmidt procedure. And so here the inner product I have in mind is this one. So we're just considering the polynomials as functions on the interval from -1 to 1. So that's perfectly fine. We can take them as functions on whatever interval we like, depending on the problem at hand. So let's see. So for the first step, we'll take our first function, so this one, and normalize it. So let's see. So we've got 1. Now the magnitude of 1 with respect to this inner product is the integral from -1 to 1 of 1 squared, which is just 1. And when we integrate it from -1 to 1, we get 2. So that tells us that we should take our first basis vector to be 1 over root 2. All right. Now we go on to the next one. And so for the next one, let's see, so we're going to take x, and then we're going to subtract off its projection to E0. So that's going to look like x minus, and then let's see, so it's projection, so this is going to be the integral from -1 to 1 of x times E0, which was 1 over root 2. And here, maybe this would be clearer if I made these into t's. And then times 1 over root 2. And so when you work that out, well, what do we have? We've got that this is an odd function. It's just a scalar multiple of t. And we're over a balanced interval from -1 to 1. So that whole thing is going to give us 0. So we have x minus 0, or x. So that's going to be the numerator for our second guy. We need to check the norm of this element. So norm squared of x is integral from -1 to 1 of t squared dt. And so that's going to be t cubed over 3 evaluated from -1 to 1, so we get a positive third and a negative third gives us a total, a positive third minus a negative third gives us a total of 2/3. So we're going to have to normalize by square root of 3 over 2. All right. Now for our next one, we're going to be looking at x squared minus its projection onto the first two. And so let's see, so we've got x squared minus, and then we'll have the integral from -1 to 1 t squared times 1 over root 2 dt times 1 over root 2. And then we'll be subtracting, actually maybe it sort of looks better if I put the parenthesis in there. Okay, so I'm just writing it like this so you can see that this part here is the scalar. And then this part out back is the vector itself. Okay. And then we're going to be subtracting, let's see, so the integral from -1 to 1 of t squared, and then the one we found in the last step. So that's going to be root 3 over 2t. And then that's going to be times root 3 over 2t. And so again, this foregoing bit here is x against E1 in the inner product, and then this latter part here is E1, oops, except faulty notation outside, I'm denoting it with an x after we finish integrating. Okay, So let's see, the combination of these guys here is going to be a t cubed, which is odd. So that whole thing is going to get dead. And I've just got that first part. So this is going to end up giving me x squared minus 1/3. And then I need to figure out what the magnitude of x squared minus 1/3 is. So I'll compute its square. So that's the integral from -1 to 1 of, and then I've got multiplying out x squared minus 1/3 times itself. I get x to the 4th minus 2/3 x squared plus 1/9. And then, let me, I confuse myself switching back and forth between t's inside the integral and x's outside the integral. But that's going to give me 8/45. So then my E2 is going to be 45/8 in the square root times x squared minus 1/3. And so on and so forth. So the functions that I got here, so 1/√2, and then √3/2x, and then √45/8 x squared minus 1/3. That is a orthonormal basis for P2 with this inner product. And if I wanted to, I could just carry on with this this procedure and get more. These, by the way, if you're interested, these things here are called the Legendre polynomials. And they've been around since, I think, 1782 or something like that, when they were discovered by probably somebody other than Lagrange, because everything in mathematics is named incorrectly. But they pop up in various physics aspects or problems, like stuff having to do with gravitational or electrostatic potential and stuff like that. More recently, they've actually been used in neural networks. They have some sort of advantages there. This is Legendre polynomials are just one of a large family of orthogonal polynomials. And it turns out that for absolutely no coincidence, that orthogonal polynomials are often associated with second-order differential equations. It actually turns out that they are eigenfunctions of Sturm-Liouville eigenproblems. And so there's a whole bunch of these classes of differential equations problems that produce, as solutions, families of orthogonal polynomials. And because of this, there's all sorts of crazy relationships, because you get all this orthogonality coming out and this and that, and they're eigenfunctions of a differential operator and blah, blah, blah. So it's a big, long, fat, hairy story. I hardly recommend that you look up the Wikipedia page for orthogonal polynomials or Legendre polynomials in particular. There's also some other orthogonal polynomial families that are well known. There's the Laguerre and the Hermite and the Chebyshev, which can be spelled about 12 different ways depending on who you ask. And there are a whole lot of others. And they all have interesting recurrence relations and tales from physics and so on and so forth.